So here's something worth thinking about as you settle in tonight. Every bridge you've ever driven across, every building you've ever walked into, every plane you've ever sat inside, someone had to figure out how to make that thing not fall apart. And the truth is, a lot of the time, we only learned how to make things work because we first watched them fail. Spectacularly, sometimes tragically, and often in ways that no one saw coming. That's what we're going to talk about tonight. Not to be grim about it, but because there's something genuinely fascinating about the way engineering disasters have shaped the world we live in. Every safety regulation, every building code, every redundant system in the airplane above your head, those rules were almost always written in response to something going wrong. Someone made a choice, or missed a detail, or trusted a material that wasn't ready to be trusted, and the consequences taught us something we couldn't have learned any other way. There's a saying among engineers that the history of engineering is the history of failure. And it sounds cynical, but it's actually kind of beautiful when you think about it. It means we learn, we adapt, we build the next one better. And the story goes back a lot further than you might expect. We tend to think of engineering disasters as a modern phenomenon: collapsed highway overpasses, exploding space shuttles, that kind of thing. But people have been building ambitious structures for thousands of years, and they've been watching those structures come down for just as long. Let's start way back. Ancient Rome. Around the year 27 AD, in the town of Fidenae, just a few miles north of Rome, a man named Attilius decided to build an amphitheater. Now, Rome had the Colosseum. Well, actually, the Colosseum wouldn't be built for another few decades, but Rome had permanent stone amphitheaters. Fidenae did not. Attilius was an entrepreneur, a freedman, which meant he was a former slave, who had gained his freedom and was looking to make money, and he figured that if he built a big wooden amphitheater and hosted gladiatorial games, people would come from all over. He was right about that part. What he got wrong was pretty much everything else. According to the Roman historian Tacitus, Attilius didn't lay a proper foundation. He didn't secure the wooden superstructure adequately. He built it fast, and he built it cheap because the whole point was profit. And when the games began, somewhere around 50,000 people packed into this thing. 50,000. In a wooden structure built by a man with no apparent engineering expertise and every incentive to cut corners. You can probably guess what happened. The amphitheater collapsed. The upper tiers gave way, and the whole structure folded inward and outward simultaneously, crushing and trapping thousands of spectators. Tacitus says the death toll was around 20,000 people, though some estimates put it even higher, 20,000. To put that in perspective, that would make it one of the deadliest structural failures in all of recorded history, and it happened almost 2,000 years ago. Now here's the thing that matters from an engineering standpoint. After the disaster at Fidenae, the Roman Senate passed new regulations. They required that anyone building an amphitheater had to have their foundation soil examined. They set minimum wealth requirements for the builders, which was a crude way of ensuring that the person funding the project had enough resources to do it properly and enough to lose if they didn't. It was, in a very real sense, one of the first building codes in Western history, born directly from catastrophe. And that pattern, disaster, investigation, regulation, is a pattern you'll see repeated over and over and over again throughout the next 2,000 years. It's almost like a rhythm. Someone pushes the boundaries of what's possible. Something goes wrong. People figure out why. And then the rules change so it doesn't happen again. until someone pushes the boundaries again. Think about what that means for a second. It means that engineering progress isn't just a story of brilliant people having brilliant ideas. It's also a story of things breaking, and of the painful, methodical work of understanding why they broke. And sometimes the people who contributed the most to engineering knowledge aren't the ones who built the thing that stood. They're the ones who built the thing that fell, because the falling taught us something the standing never could. Let's jump forward quite a bit. Past the Middle Ages, past the Renaissance, past all those centuries of cathedrals and aqueducts and fortifications, many of which did fail in their own interesting ways. Let's land in the early 19th century, because that's when things really start to accelerate. The Industrial Revolution is in full swing. Iron is becoming a structural material. Steam power is changing everything. And suddenly, engineers are being asked to build things at a scale and speed that humanity has never attempted before. Bridges, especially. The 19th century was obsessed with bridges. Rivers were the highways of commerce, but they were also the barriers, and the railroad was coming, and the railroad needed to cross those rivers. So bridge building became one of the most important, most prestigious, and most dangerous engineering disciplines in the world. And here's where we meet one of the most instructive early disasters of the industrial age. It's December 28th, 1879, a Sunday evening in Scotland. The Tay Bridge, which spans the Firth of Tay between Dundee and the suburb of Wormit, has been open for less than 2 years. It's the longest bridge in the world at the time, over 2 miles long, with 85 spans carrying a single railroad track across the wide, wind-swept estuary. The bridge was designed by Thomas Bouch, and Bouch was knighted for it. Queen Victoria herself rode across it. It was considered a triumph of Victorian engineering, and on that Sunday evening, a passenger train with about 75 people aboard entered the bridge from the south end during a violent storm. The wind that night was extraordinary. Estimates vary, but it was likely blowing at somewhere between 60 and 80 miles per hour, with gusts possibly exceeding that. The train moved onto the bridge's high girder section. That's the central portion where the track ran inside enclosed iron girders, raised high above the water to allow ships to pass underneath. And as the train reached that section, the high girders collapsed. 13 spans, the train, and everyone aboard plunged into the freezing water of the Tay. There were no survivors. Now, the immediate cause was the wind. But the real cause, the engineering cause, was much more complicated and much more human. When investigators examined the wreckage, they found problems everywhere. The cast iron columns that supported the high girders had been manufactured with flaws, blowholes and imperfections in the casting that had been filled in with a putty-like material called Beaumont's egg, essentially a mixture of beeswax, iron filings, and other stuff that was used to cosmetically hide defects. The columns looked fine on the outside. Inside, they were compromised. But it went deeper than that. Thomas Bouch, in his original design, had made inadequate provision for wind loading. This is a crucial concept, so let's sit with it for a moment. When you build a tall structure, especially one that stretches across a wide open body of water, the wind pushes against it sideways. That sideways force is called wind load, and you have to design your structure to resist it. Bouch had used a wind pressure figure of about 10 pounds per square foot in his calculations. The Board of Trade's own Astronomer Royal for Ireland, a man who advised on such things, had suggested that figure. But the actual wind pressures during a severe storm on the Tay could be several times higher than that. The bridge simply wasn't strong enough laterally. It couldn't handle the sideways push of a major gale. And here's where the human story gets really poignant. Thomas Bouch was, by all accounts, devastated. He had been working on an even more ambitious project, a bridge across the Firth of Forth, further south. After the Tay Bridge disaster, that commission was taken away from him. His reputation was destroyed. The Court of Inquiry's report was damning, essentially placing the blame squarely on his design. Bouch died less than a year later, in October 1880, at the age of 58. His friends said he died of a broken heart, though the medical reality was probably more complicated than that. But the timeline is hard to ignore. The bridge fell, and then he fell. And yet, here's what came out of it. The Tay Bridge disaster forced the entire engineering profession to take wind loading seriously in a way it never had before. The replacement Tay Bridge, which still stands today and still carries trains, was designed with vastly greater wind resistance, and the Forth Bridge, the one Bouch lost, was redesigned from scratch by Benjamin Baker and John Fowler, and they built one of the most iconic structures in the world. That massive red cantilever bridge, the one you've probably seen in photographs even if you've never been to Scotland, was deliberately over-engineered. Baker and Fowler were so determined to prove that their bridge could handle anything nature threw at it that they made it almost absurdly strong. The Forth Bridge used more than 50,000 tons of steel and was, for its time, the most robust, large-scale structure ever built. It was a direct reaction to the Tay Bridge collapse. Every rivet in that bridge carries the memory of what happened upstream, so you see the pattern already forming. Ambition, failure, understanding, and then a leap forward. The Tay Bridge had to fall so the Forth Bridge could stand. That's a brutal kind of progress, and it cost 75 people their lives, and it's important to hold that cost clearly, even as we appreciate what was learned. But the 19th century wasn't done teaching these lessons. Not even close. Because as bridges were getting longer and taller, something else was happening that would create an entirely new category of engineering disaster. Factories were getting bigger. Boilers were getting more powerful. Machines were spinning faster. And the materials, the iron, the early steel, were being pushed into service in ways that no one fully understood yet. Think about what it means to not fully understand your materials. Today, we have materials science as an entire discipline. We can model the behavior of steel under stress down to the molecular level. We know about fatigue, about creep, about brittle fracture, about stress, concentration. But in the 1800s, a lot of that knowledge simply didn't exist yet. Engineers were working with iron and steel the way a chef might work with a new ingredient they'd never tasted. They had some intuition, some rules of thumb, but they didn't really know what would happen when they pushed things to the limit. And that uncertainty, that gap between ambition and understanding, is where disasters live. It's the space where engineers reach beyond what they can prove, sometimes because they're arrogant, sometimes because they're under pressure, and sometimes simply because the knowledge they need hasn't been discovered yet. No one can account for a phenomenon that hasn't been named. Which brings us to something that happened in a completely different domain, something that would reshape how engineers thought about repeated stress and hidden weakness. In the early days of railroad expansion, there was a problem that kept showing up and that nobody could quite explain. Railroad axles were breaking. Not new axles that had been in service for a while, carrying loads well within their supposed capacity. An axle would be fine for months or years, and then one day, without warning, it would snap. Wheels would come off. Trains would derail. People would die. A German mining engineer named Wilhelm Albert had noticed something similar with mine hoist chains as early as the 1830s. Chains that were well within their load limits would eventually break if they were flexed back and forth enough times. But it was another German engineer, August Wöhler, working in the 1850s and 1860s, who really cracked the problem open. Wöhler conducted years of systematic experiments on metal specimens, subjecting them to repeated cycles of stress, bending them back and forth, over and over, thousands and thousands of times. And what he found was something genuinely unsettling. Metal could fail at stress levels far below its breaking strength, far below, if that stress was applied and removed enough times. A steel bar that could hold, say, 10,000 pounds without bending permanently might snap clean in two under a load of only 3,000 or 4,000 pounds if you cycled that load on and off tens of thousands of times. The metal didn't look damaged. It didn't visibly deform. It just broke, as if it had been keeping a secret, accumulating invisible damage deep inside its structure with every single cycle, until one day it had nothing left to give. Wöhler mapped this out meticulously. He created what we now call SN curves, stress versus number of cycles, and those curves told a story that changed engineering forever. For any given material, there was a relationship between how hard you pushed it and how many times you could push it before it failed. Push it hard, and it fails quickly. Push it gently, and it lasts much longer. And for some materials, particularly steel, there appeared to be a threshold, a stress, level below which you could theoretically cycle the load forever, and the material would never fail. That threshold became known as the endurance limit, or the fatigue limit. It was, in a sense, the material's comfort zone. Stay below it, and you're safe. Creep above it, even a little, and the clock starts ticking. Now think about what this meant practically. Every bridge that carries traffic, every railroad axle that turns, every aircraft wing that flexes in turbulence, these are all structures experiencing repeated loading. Not one big dramatic overload, but thousands, millions, sometimes billions of small stress cycles. Wöhler had discovered that the way things break in the real world is usually not through one catastrophic moment of excess. It's through the quiet, patient accumulation of tiny insults, which is a pretty profound idea if you sit with it for a moment. The thing that gets you isn't the storm. It's the 10,000 gentle breezes. And here's what's really important about this discovery. It didn't just explain why railroad axles were breaking. It gave engineers a framework, a way of thinking about structural life. Before Wöhler, you designed something to be strong enough. After Wöhler, you had to design something to be strong enough for long enough. Time and repetition became part of the equation. And that shift in thinking, from static strength to fatigue life, would become one of the most critical ideas in all of engineering. It would take decades for the full implications to sink in, and along the way, a lot of people would pay the price for that slow absorption. But let's stay with the 19th century for a bit longer, because there's another disaster from this era that deserves real attention. One that's less about material fatigue and more about something equally dangerous: the gap between what an engineer designs and what actually gets built. And for that, we need to talk about the Ashtabula River Railroad disaster of 1876. On the evening of December 29th, 1876, a bitterly cold night, temperatures well below zero, a passenger train called the Pacific Express was crossing an iron bridge over the Ashtabula River Gorge in northeastern Ohio. The bridge was about 150 feet long, a Howe truss design, and it had been in service for roughly 11 years. The train was heavy, 2 locomotives pulling 11 cars packed with passengers heading home after the holidays. As the second locomotive reached the far side of the bridge, the structure gave way. The entire span collapsed into the gorge, about 70 feet below. The cars piled on top of each other in the ravine, and then, and this is the truly horrific part, the heating stoves inside the wooden passenger cars ignited the wreckage. Fire consumed the twisted pile of wood and iron. 92 people died, many of them burned beyond recognition. It was one of the deadliest railroad disasters in American history up to that point. The investigation that followed was messy and contentious. The bridge had been designed by Amasa Stone, a powerful railroad executive and self-taught engineer who was also the president of the Lakeshore and Michigan Southern Railway, the very company that owned the bridge. Stone had insisted on his own design modifications, reportedly overriding the concerns of professional engineers. The bridge used cast iron where wrought iron would have been more appropriate. Cast iron, you'll remember from the Tay Bridge story, is strong in compression. It handles being squeezed, but it's brittle and weak in tension. It doesn't stretch, it snaps. In a truss bridge, some members are in compression and some are in tension. And using the wrong material for a tension member is a recipe for exactly the kind of sudden failure that happened that night. The investigation pointed to a failure in one of the bridge's diagonal braces, likely a cast iron member that cracked under the combined weight of the heavy train and the stress of the cold, because cold makes brittle materials even more brittle. Stone defended his design fiercely. He had powerful friends. The official inquiries were somewhat inconclusive, muddied by politics and influence. But the engineering community knew. They understood what had gone wrong. And Amasa Stone, despite his wealth and his connections, never fully escaped the shadow of that night. He took his own life in 1883, 7 years after the disaster. It's a grim story, and I mention it not for the sensationalism, but because it illustrates something that comes up again and again in engineering disasters. The danger of concentrating too much authority in one person, especially when that person has both the power to make decisions and the pride to resist being questioned. This is a pattern you'll see repeated throughout history. A strong personality pushes through a design or a decision, and the institutional checks that should catch errors, peer review, independent inspection, the simple act of someone saying, "Wait, are we sure about this?" Those checks get overridden by ego or authority or economic pressure. The engineering itself might be flawed, but the deeper failure is organizational. It's human. And it's one of the hardest problems in engineering to solve, because you can't fix it with better steel or stronger concrete. You have to fix it with culture, with processes, with the willingness to listen to the person in the room who's raising their hand and saying, "Something doesn't feel right." So by the late 1800s, you've got this accumulating body of painful lessons. The Romans learned that you need building codes. The Tay Bridge taught the British that wind loads matter and that hidden defects in castings can kill. Wöhler showed that materials have a memory for stress, that repeated loading is a silent killer. Ashtabula demonstrated the danger of unchecked authority and wrong materials in wrong places. Each disaster was adding a brick to the wall of engineering knowledge. But here's the thing. That wall was being built slowly, and the lessons were often local. What one railroad learned from a bridge collapse in Ohio didn't necessarily reach the engineers building a different bridge in Scotland. There was no global system for sharing failure data, no international standards body, no universal engineering code. Knowledge was fragmented, siloed, passed along through apprenticeships and professional societies and word of mouth. And meanwhile, ambition kept accelerating. The 20th century was coming, and with it, a scale of construction and a pace of technological change that would make everything that came before look almost quaint. Steel was getting better, cheaper, more available. Concrete was being reinforced with iron and steel rods, creating a composite material that could handle both compression and tension. Buildings were getting taller, bridges were getting longer. And then, of course, humans decided they wanted to fly. But before we get to the air, let's talk about one more earthbound disaster that perfectly captures this transition from the 19th to the 20th century. One that happened in a city that was trying, with enormous energy and optimism, to reinvent itself. On January 15, 1919, in Boston's North End neighborhood, a storage tank holding 2.5 million gallons of molasses burst open. The tank was 50 feet tall, 90 feet in diameter, made of steel plates riveted together, and it had been built in a hurry during World War I to supply the production of industrial alcohol. When it failed, a wave of molasses, and we're talking about a wave estimated at 15 to 25 feet high, moving at roughly 35 miles per hour, surged through the narrow streets of the North End. 21 people were killed. 150 were injured. Buildings were knocked off their foundations. A section of the elevated railway was buckled. Horses, dogs, and cats were trapped and drowned in the viscous flood. It sounds almost absurd. Death by molasses. And for years it was treated as a kind of dark joke. But the engineering failure was dead serious. The tank had been leaking since the day it was built. Residents had been collecting the molasses that seeped through the seams. The company's response to the leaking was to paint the tank brown so the leaks would be less visible. That detail alone tells you something about the culture of the time. The tank had been designed without adequate engineering review. The steel plates were too thin for a structure that size holding a liquid that dense. Molasses is significantly heavier than water, about 1.5 times as dense, and the tank's walls needed to withstand enormous hydrostatic pressure. The riveted joints were poorly constructed, and critically, the tank had never been properly tested. It was never even filled with water first to check for leaks, which was standard practice even then. The legal case that followed the Great Molasses Flood, as it came to be known, was a landmark. It dragged on for years. Over 3,000 pages of testimony, over 1,000 witnesses. The court appointed an independent auditor, an engineering professor, to review the technical evidence. And the conclusion was clear. The tank had been structurally inadequate from the beginning. The company, United States Industrial Alcohol, was found liable. But more importantly, the case helped establish the principle that engineering projects required proper review, that you couldn't just throw up a structure without having someone qualified verify that the design was sound. This is something we take completely for granted today. You can't build a house, let alone a storage tank or a bridge, without permits and inspections and stamped engineering drawings. But in 1919, those requirements were still patchy, still evolving. The molasses flood helped push Boston and eventually other cities toward stricter building codes and mandatory engineering certification. It's one of those disasters where the thing that failed wasn't exotic or cutting edge. It was just a tank, a big steel cylinder holding liquid. The physics weren't complicated. The failure wasn't mysterious. It was simply that nobody with the right knowledge had been required to check the work. And that's a theme worth holding on to as we move forward. Because the 20th century is about to bring us into an era where the engineering gets genuinely complex, where the physics are harder, where the materials are newer, where the systems interact in ways that nobody fully understands, When your structure is a simple tank and you skip the engineering review, you get a flood of molasses. But when your structure is a pressurized aircraft fuselage flying at 30,000 feet and you miss something in the design, the consequences unfold in a very different way. And that's exactly what happened in the early 1950s, when the world's first commercial jet airliner, a beautiful, ambitious, revolutionary machine called the de Havilland Comet, started falling out of the sky, and nobody could figure out why. And that mystery, the sheer bafflement of it, is what makes the comet story one of the most important chapters in the entire history of engineering failure. So let's stay with it for a while. The de Havilland Comet was, by every measure, a marvel. It first flew in 1949, and it entered commercial service with BOAC, British Overseas Airways Corporation, on May 2, 1952, flying from London to Johannesburg with stops along the way. And you have to understand what this meant at the time. Propeller-driven airliners were loud, slow, vibrating things that took forever to cross an ocean. The Comet was something else entirely. It was sleek, it was fast, it was pressurized to fly above the weather at altitudes that propeller planes couldn't comfortably reach, and it was powered by 4 de Havilland Ghost turbojet engines buried elegantly inside the wing roots. Passengers described the experience as almost surreal. The smoothness, the quiet compared to piston engines, the sense of gliding. Britain was enormously proud of it. This was a country still rebuilding from the war, still rationing some foods, and here it was leading the world into the jet age. The Americans didn't have anything like it yet. The Boeing 707 was still years away. For a brief, shining moment, Britain owned the future of aviation. And then things started going wrong. In the first year of service, there were a few incidents: a takeoff accident in Rome, a failure to get airborne in Karachi, that were attributed to pilot handling of the new type. Concerning, but not necessarily pointing to a fundamental design flaw. But then, on May 2nd, 1953, exactly 1 year after the Comet entered service, BOAC Flight 783 broke apart in a severe storm shortly after takeoff from Calcutta. All 43 people on board were killed. The investigation concluded that the aircraft had likely encountered extreme turbulence and suffered structural failure of the wings or tail. Modifications were made. The fleet kept flying. Then, on January 10, 1954, BOAC Flight 781 departed Rome bound for London. About 20 minutes after takeoff, cruising at around 26,000 feet over the Mediterranean near the island of Elba, the aircraft simply disintegrated. 35 people died. Wreckage fell into the sea. And now there was real fear, because this wasn't a storm. The weather had been fine. The aircraft had just come apart. The Comet fleet was grounded. De Havilland and the British government launched an investigation. They examined every system they could think of. They checked the engines, the fuel system, the flight controls. They made over 60 modifications to the aircraft. After 2 months, confident that they'd addressed the possible issues, they returned the Comet to service. And here's where the story becomes genuinely haunting, because just 16 days later, on April 8, 1954, another Comet, South African Airways Flight 201, broke apart over the Mediterranean near Naples. 21 people killed. Same profile. Cruising altitude. Good weather. Catastrophic. Instantaneous structural failure. The Comet was grounded permanently, and the British government ordered what would become one of the most exhaustive engineering investigations in history, led by the Royal Aircraft Establishment at Farnborough. The question was deceptively simple. Why were these aircraft breaking apart in mid-air? The answer would change how every pressurized aircraft in the world is designed, tested, and maintained, right up to the plane you last flew on. Now, here's the thing about investigating an aircraft that fell into the Mediterranean. You need the wreckage. And in 1954, deep-sea recovery was nothing like what it is today. There were no remotely operated submersibles, no sophisticated sonar mapping. The Navy literally sent ships to drag the seafloor near Elba, pulling up pieces of Flight 781 from about 500 feet of water. It took months. They recovered about 70% of the airframe, and they laid it out in a massive hangar at Farnborough, painstakingly reassembling the jigsaw of torn aluminum on a wooden frame, trying to read the story written in the pattern of the fractures. Meanwhile, they did something else, something brilliant and unprecedented in scale. They took a complete Comet airframe, one that had already accumulated some flight hours, and they built a giant water tank around the fuselage section. Then they began pressurizing and depressurizing it with water, over and over and over again, simulating the pressure cycles that the aircraft would experience in normal service. Every time a jet climbs to cruising altitude, the cabin is pressurized to keep the passengers comfortable. The pressure inside is significantly higher than the thin atmosphere outside, and every time it descends and lands, that pressure equalizes. So each flight is one pressure cycle. The fuselage swells slightly, then relaxes. Swells, relaxes. They used water instead of air because if the fuselage failed while pressurized with air, the explosive decompression would destroy the evidence. Water doesn't compress the same way. A failure would be contained, observable, studiable. They ran this test around the clock. And after the equivalent of about 9,000 flight hours, which corresponded to roughly 3,000 pressurization cycles, the fuselage failed. A crack appeared and ripped open. And when they examined where it started, they found it had originated at the corner of a window, specifically at one of the square-cornered windows that were a distinctive design feature of the Comet. And this is where August Wöhler's work, from nearly a century earlier, comes roaring back into the story. Remember metal fatigue, the idea that a material can fail well below its ultimate strength if it's subjected to repeated cycles of stress? That's exactly what was happening. Every pressurization cycle was stressing the fuselage skin, and at the corners of those square windows, the stress wasn't evenly distributed. It concentrated. Think about it this way. If you take a sheet of paper and cut a small round hole in it, then pull the edges, the paper will stretch fairly evenly around the hole. But if you cut a square hole with sharp corners and you pull the same way, the paper wants to tear right at those corners. The stress flows around the hole like water flowing around a rock in a stream, and at a sharp corner, that flow gets pinched into a tiny area. The stress at that point can be 2, 3, even 4 times higher than the average stress in the surrounding material. The Comet's fuselage was experiencing this stress concentration at every window corner, every single flight. And the aluminum skin was accumulating microscopic fatigue damage, cycle after cycle, until a tiny crack formed. Once that crack existed, it became its own stress concentrator. The tip of a crack is incredibly sharp, and the stress at that tip is enormous. So the crack grew a tiny bit with each subsequent flight, and then, at some critical length, the crack became unstable. It propagated across the fuselage at the speed of sound in the metal, essentially instantaneously, and the pressurized cabin burst open like a balloon. The aircraft disintegrated. The Farnborough investigation confirmed this, by examining the recovered wreckage from the Elba crash. They found the origin point, a fatigue crack at the corner of an automatic direction finder window on the top of the fuselage, near a row of rivet holes that created additional stress concentrations. The crack had grown slowly through maybe 70% of the skin thickness before the final, catastrophic rupture. It was all there in the fracture surfaces, readable like tree rings if you knew what to look for. The smooth, burnished region where the crack had grown slowly over many cycles, and then the rough, crystalline region where it had torn apart all at once. Here's what's really sobering about this. De Havilland had tested the Comet's fuselage before it ever flew. They had pressurized a test cabin to double the normal operating pressure and held it there, and it survived. They believed this proved adequate strength, and by the standards of the day, it did. But a static pressure test, one big squeeze, tells you nothing about fatigue. It tells you the structure is strong enough for one cycle. It doesn't tell you what happens after 3,000 cycles, when those microscopic cracks have been quietly growing in the dark. The Comet's designers weren't negligent. They were working at the edge of what was understood. Pressurized jet flight at high altitude was genuinely new territory. Nobody had accumulated enough experience with pressurization cycling at those stress levels to know that fatigue would be the critical failure mode. The knowledge existed in theory. Wöhler had laid the groundwork decades earlier, but it hadn't been fully translated into aircraft design practice for this specific scenario. And this is one of those moments where a disaster doesn't just fix one airplane, it transforms an entire industry. After the Comet investigation, everything changed. Aircraft fuselages were redesigned with rounded windows and rounded corners on all cutouts. Look at any airplane window today, and you'll see those characteristic oval shapes with generous radii. That's the Comet's legacy, written into the geometry of every commercial aircraft in the world. Fatigue testing became mandatory and exhaustive. New aircraft types now undergo tens of thousands of simulated pressurization cycles before they're certified. The concept of damage tolerance was born. The idea that you assume cracks will form, and you design the structure so that a crack can exist and grow slowly enough to be detected during routine inspections before it ever reaches a dangerous length. You build in crack stoppers, reinforcing straps that arrest a running crack before it can unzip the fuselage. You establish inspection intervals based on how fast cracks are expected to grow. Think about what that means philosophically. Before the Comet, the engineering mindset was essentially, make it strong enough and it won't break. After the Comet, the mindset shifted to, assume it will develop cracks and design it so those cracks don't kill anyone. That's a profound change. It's the difference between hoping for perfection and planning for imperfection. And that second approach, that humility, turns out to be far safer. The Comet story also illustrates something else we've been circling around, the cost of being first. De Havilland paid an enormous price for leading the jet age. The Comet was eventually redesigned as the Comet 4, with oval windows and a thicker, more fatigue-resistant fuselage, and it re-entered service in 1958. But by then, Boeing had learned from every single one of de Havilland's painful lessons. The 707, which entered service the same year, incorporated all of the fatigue knowledge gained from the Comet investigations. Boeing got to build on someone else's tragedy. The 707 became the dominant jet airliner. The Comet 4, despite being a fine aircraft, never recovered commercially. Britain's lead in the jet age evaporated. Now, you might think that after the Comet, the aviation industry had fatigue figured out. And in many ways it did, for pressurized fuselages. But fatigue is sneaky. It shows up wherever there are repeated loads, and aircraft experience repeated loads everywhere. Wings flex up and down with every gust, every maneuver, every landing. Engine mounts vibrate. Landing gear cycles through extension and retraction. And sometimes, even with all the lessons learned, something slips through. Which brings us to a different kind of engineering disaster. One that happened not because the physics were unknown, but because the system for communicating critical information broke down. On April 28, 1988, Aloha Airlines Flight 243 was cruising at 24,000 feet over the Pacific when an 18-foot section of the upper fuselage simply tore away. The cabin depressurized explosively. One flight attendant, Clarabelle Lansing, was swept out and lost. 65 other people were injured. And yet, remarkably, the pilots managed to land the aircraft. The photographs are extraordinary. The plane on the ground with a massive section of its roof simply gone. Passengers visible from outside. The structure peeled back like a sardine can. This was a 19-year-old Boeing 737 that had operated in the Hawaiian island hopping market. And here's the critical detail. Short flights mean more pressurization cycles per flight hour. This particular aircraft had accumulated nearly 90,000 pressurization cycles, far more than a typical 737 of the same age that flew longer routes. The fuselage skin had developed widespread fatigue cracking along the rivet lines, where the overlapping sheets of aluminum were bonded and fastened together. The bonding adhesive had deteriorated over time, especially in the warm, salty Hawaiian environment, transferring more load to the rivets, which accelerated fatigue cracking. Multiple small cracks had linked up into one long crack, and then the whole thing unzipped. That's the word investigators used, unzipped, because that's exactly what happened. Once those individual cracks linked together past a critical length, the skin couldn't contain the pressurization load anymore, and it tore open along the rivet line like a zipper being pulled. The structural concept that failed here has a name, and it's worth knowing: multi-site damage. Before Aloha 243, the fatigue models used in aviation were mostly concerned with a single dominant crack growing from a single stress concentration, like the corner of a window on the Comet. You find the most likely crack initiation site. You predict how fast a crack will grow from that point. You schedule inspections to catch it before it reaches a dangerous size. That's damage tolerance in a nutshell. But multi-site damage is different. It's not one crack you're looking for. It's dozens, maybe hundreds, of tiny cracks all growing simultaneously along a row of fasteners. Each one individually might be well below the critical length. Each one might be nearly invisible during a visual inspection, but when they're close enough together, the little bridges of intact metal between them, engineers call those ligaments, get overstressed and snap, and suddenly you don't have 50 small cracks anymore. You have one enormous crack, and that transition can happen fast. Catastrophically fast. The investigation into Aloha 243 was conducted by the National Transportation Safety Board, and what they found wasn't a mystery of physics. The fatigue mechanism was well understood. What had failed was the system, the web of inspections, maintenance directives, and communication that was supposed to catch exactly this kind of aging before it became dangerous. Boeing had known about potential bonding problems in early 737 fuselage lap joints. There had been service bulletins. There had been bin service bulletins. There had been inspection recommendations. But the language of those recommendations, the way they were categorized, and the way airlines interpreted their urgency, all of that was muddier than it should have been. Aloha Airlines had performed inspections, but the inspections hadn't caught the extent of the cracking. Some of the cracks were hidden under repair doublers. Some were so small they were missed during visual checks. And the airline's maintenance program, while technically in compliance with the minimum requirements, wasn't calibrated for the unusual stress that high-cycle, short-haul operations placed on the airframe. Here's the thing that makes Aloha 243 so important in the history of engineering disasters. It wasn't a failure of knowledge. It was a failure of implementation. The right information existed. The right engineering understanding existed. But the chain from knowledge to action had weak links, and those weak links almost killed 101 people. In the aftermath, the FAA launched the Aging Aircraft Program, which fundamentally changed how regulators and airlines think about older aircraft. New mandatory inspection requirements were introduced specifically targeting multi-site damage. Airlines operating high-cycle aircraft had to do more frequent, more thorough structural inspections. And the whole concept of a damage tolerance-based maintenance program got a serious upgrade, because Aloha proved that damage tolerance only works if your inspections are actually capable of finding the damage you're tolerating. There's a quiet lesson in that, and it's one that echoes through almost every disaster we've talked about tonight. The engineering can be brilliant. The science can be sound. But if the system around the engineering, the inspections, the regulations, the communication between the people who know and the people who build and maintain, if that system has gaps, the physics will find them. Every time. Now let's shift gears a little. We've been spending a lot of time in the air, and for good reason. Aviation has one of the richest and most instructive failure histories of any engineering discipline. But some of the most devastating engineering disasters have happened much closer to the ground, and they involve something you might not think of as particularly dangerous: the places where people live and work. Buildings, structures that just sit there. You'd think getting a building to stand up would be, by the 20th century, a solved problem, and mostly it is. But mostly is a word that should make any engineer nervous. On July 17, 1981, at the Hyatt Regency Hotel in Kansas City, Missouri, 2 suspended walkways collapsed into a crowded atrium lobby during a tea dance. 114 people were killed, and over 200 were injured. It remains one of the deadliest structural failures in American history, and the engineering mistake that caused it is so simple, so seemingly minor, that it haunts every structural engineering student who learns about it. The atrium of the Hyatt Regency was a grand open space, several stories tall, and suspended across it at the 2nd and 4th floor levels were walkways, skywalks they called them, that connected different wings of the hotel. These walkways were hung from the ceiling structure by steel rods. In the original design, a single continuous rod was supposed to run from the ceiling all the way down through both walkways. The 4th floor walkway would hang from the rod at one point, and the 2nd floor walkway would hang from the same rod further down. Think of it like a thread with 2 beads on it, each bead resting on a knot. The load from the 2nd floor walkway would travel up the rod, past the 4th floor walkway, and into the ceiling structure. The 4th floor connection would only carry the weight of the 4th floor walkway itself. But during construction, a change was made. Instead of one continuous rod, the design was modified to use 2 separate rods. One rod would go from the ceiling to the 4th floor walkway. A second, separate rod would hang from the 4th floor walkway down to the 2nd floor walkway. You might think, what's the difference? And this is where it gets devastating, because the difference is everything. In the original design, the connection at the 4th floor only had to support the 4th floor walkway. But in the revised design, That same connection now had to support both walkways, because the second-floor walkway was hanging from the fourth-floor walkway, not from the ceiling. The load on that fourth-floor connection had effectively doubled, and the connection detail, a steel rod passing through a box beam with a nut and washer underneath, wasn't designed for double the load. It was barely adequate for the original load. So on that July evening, with the walkways crowded with people dancing and watching the festivities below, the fourth-floor connection failed. The nut pulled through the bottom flange of the box beam, and both walkways, the fourth floor and the second floor beneath it, came crashing down into the lobby. The change from one continuous rod to two offset rods seems like a minor construction detail, and that's precisely what makes it so instructive. It wasn't a radical redesign. It was the kind of change that happens on construction projects all the time. A fabricator calls the engineer and says, "Hey, threading a single rod through both walkways is going to be really difficult to build. Can we do it this way instead?" And somewhere in that communication, the structural implications weren't fully analyzed. The change was approved. The load path shifted, and nobody caught it. The investigation found that even the original design had problems. The connection detail was probably only at about 60% of the required capacity for the original loading. The design change roughly doubled the load, pushing it to something like 30% of what was needed. The margin wasn't just thin. It was gone before the first person ever stepped onto that walkway. It had been surviving on the fact that the walkways were never fully loaded, until they were. The aftermath was severe, and not just in human terms. The engineers of record lost their licenses. The case became a landmark in engineering ethics. It drove home a principle that every engineer learns now, but that apparently needed to be written in tragedy. When a design change is proposed, no matter how small it seems, you have to trace the load path. You have to ask, where does the force go now? Because changing the way a load gets from point A to point B can transform a safe structure into a deadly one, even if the pieces look almost the same on paper. And there's something else about the Hyatt Regency collapse that's worth sitting with. The failure mode was not exotic. It wasn't some rare material defect or an unprecedented loading condition. It was a nut pulling through a piece of steel because there was too much force on it. That's about as basic as structural failure gets. The sophistication of the error was in the system, in the communication gap between designer and fabricator, in the review process that didn't catch the change, in the professional responsibility that got diffused across multiple parties until nobody owned the critical decision. It's the same pattern we saw with Aloha 243, isn't it? The physics are straightforward. The system is where the cracks form. And speaking of systems, and how they fail in ways that compound and cascade, there's another disaster from roughly the same era that takes this idea to an entirely different scale. Because sometimes it's not just one communication breakdown or one missed detail. Sometimes it's an accumulation of small decisions, each one seemingly reasonable, each one slightly eroding the safety margin until the whole thing comes apart in a way that shocks the world. And that's exactly what happened on January 28, 1986, at Kennedy Space Center in Florida, when the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members, including Krista McAuliffe, who was set to become the first teacher in space. The nation watched it happen live on television, and the engineering story behind it, the story of an O-ring, cold, weather, and a room full of engineers who tried to stop the launch but couldn't get the system to listen. That story is one of the most important engineering stories ever told. Not because the technology was the most complex, though it was staggeringly complex. But because the Challenger disaster laid bare, in the most public and painful way possible, how organizational culture can override technical knowledge, how the people who know the most about a specific risk can be the ones whose voices get lost. Let's start with the O-ring, because that's where the physics lives. The space shuttle's solid rocket boosters were enormous cylinders, about 149 feet tall, and they were manufactured in sections, segments they called them, that had to be assembled at Kennedy Space Center. Where those segments joined together, there was a joint, and that joint had to contain the incredibly hot gases produced when the solid propellant burned. We're talking about gases at roughly 5,700 degrees Fahrenheit, pressurized to nearly 1,000 pounds per square inch. If those gases escaped the joint, you had what engineers called blow-by, and blow-by was catastrophic because those superheated gases would act like a cutting torch on whatever they touched. The seal in each joint relied on a pair of rubber O-rings, primary and secondary, made from a fluorocarbon elastomer. Think of them as giant rubber bands, about 37 feet in circumference, sitting in grooves in the joint. When the booster ignited and internal pressure spiked, the joint would flex slightly, and the pressure was supposed to push the O-ring into its seat, creating a tighter seal. It's actually a clever design in principle. The higher the pressure, the harder the seal gets pushed into place. Self-energizing, they called it. But here's the thing. For that to work, the O-ring has to be resilient enough to follow the movement of the joint. It has to squish and spring back fast enough to maintain contact with the metal surfaces as the gap opens and closes during ignition. And rubber, like most materials, behaves differently at different temperatures. When it's warm, it's pliable, it bounces back quickly. When it's cold, it gets stiff. It loses that springiness. It responds more slowly. The engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, knew this. They had data. After previous shuttle flights, they'd inspected the boosters and found evidence of blow-by. Hot gas getting past the primary O-ring and sometimes reaching the secondary. This wasn't supposed to happen at all in the original design intent, but it had been happening, and NASA had gradually come to accept it. They'd even reclassified the O-ring erosion from a serious anomaly to something closer to an acceptable risk, an expected condition. And that right there is the first crack in the system. When you start normalizing something that was originally a warning sign, you're eroding your safety margin without updating your risk model. Sociologist Diane Vaughan later called this the normalization of deviance. And it's one of the most important concepts to come out of the Challenger investigation. You see it everywhere once you know to look for it. A small anomaly occurs, nothing bad happens, so it gets accepted. Then a slightly larger anomaly occurs, nothing bad happens, so that gets accepted too. Each step feels reasonable in the moment, but the baseline keeps shifting, and nobody formally decides that the new baseline is safe. It just sort of becomes the new normal through repetition. Now, the night before the Challenger launch, January 27, 1986, temperatures at Kennedy Space Center were forecast to drop into the low 20s Fahrenheit. That's extraordinarily cold for a Florida launch. The coldest previous shuttle launch had been at 53 degrees, and even that flight had shown significant O-ring blow-by. The engineers at Morton Thiokol were alarmed. Roger Boisjoli, in particular, had been raising concerns about the O-rings for months. He'd written memos. He'd presented data at meetings. He knew, from both test data and flight history, that cold temperatures degraded O-ring performance. And now They were looking at a launch in conditions colder than anything they'd ever flown in, by a huge margin. A teleconference was set up that evening between Morton Thiokol engineers in Utah and NASA managers at both Kennedy Space Center and Marshall Space Flight Center in Alabama. Marshall was the NASA center responsible for the solid rocket boosters, and the management culture there is a crucial part of this story. The Thiokol engineers presented their data and recommended against launching at temperatures below 53 degrees Fahrenheit. They showed charts correlating temperature with O-ring erosion and blow-by from previous flights. Their recommendation was clear: don't launch. And here's where the system broke down in a way that still haunts the engineering profession. NASA managers pushed back. They questioned the data. They asked Thiokol to reconsider. One NASA manager reportedly said something to the effect of, "My God, Thiokol, when do you want me to launch? Next April?" The pressure was real. The shuttle program was behind schedule. There was political visibility around this particular launch because of Krista McAuliffe and the Teacher in Space program. The launch had already been delayed multiple times. None of that should have mattered, but it created an environment where the burden of proof got flipped. Instead of Thiokol having to prove it was safe to launch, which is the correct standard, the dynamic shifted so that Thiokol had to prove it was unsafe. And proving a negative, especially with limited data points, is much harder. During a break in the teleconference, Thiokol managers huddled with their engineers. Boisjoli and his colleague Arnie Thompson argued passionately that the data supported a no-launch recommendation. But the management chain at Thiokol made a different calculation. Senior Vice President Joe Kilminster reversed the recommendation and told NASA that Thiokol now supported the launch. The engineers were devastated. Boisjoli later testified that he felt completely helpless, that he had done everything he could, and the decision had been taken away from him by people who weren't looking at the same data with the same understanding. The next morning, January 28th, the temperature at launch time was 36 degrees Fahrenheit. Think about that. 36 degrees, when the engineers had recommended against launching below 53. The O-rings in the right solid rocket booster's aft field joint were cold and stiff. When the booster ignited, the joint flexed, and the primary O-ring didn't seat properly. Hot combustion gases blew past both O-rings and began burning through the external tank. 73 seconds into flight, the lower strut connecting the right booster to the external tank failed. The booster pivoted into the tank ruptured, and the shuttle broke apart in a massive aerodynamic event. The crew cabin remained largely intact for several seconds and fell into the Atlantic Ocean from about 65,000 feet. All 7 crew members perished. The investigation that followed, led by the Presidential Commission, chaired by former Secretary of State William Rogers, commonly called the Rogers Commission, produced one of the most thorough and damning failure analyses in engineering history. And one of its most famous moments came from physicist Richard Feynman, who was a commission member. During a televised hearing, Feynman took a small piece of O-ring material, clamped it in a C-clamp, and dunked it in a glass of ice water. When he removed the clamp, the rubber didn't spring back. It just sat there, compressed, slow to recover. It was a simple, elegant demonstration of exactly the failure mechanism that had killed 7 people. Cold rubber doesn't bounce back, and in the time it takes for that joint to flex open during ignition, milliseconds, a stiff O-ring can't follow the metal surface, and hot gas gets through. Feynman also wrote a famous appendix to the Commission's report in which he contrasted NASA management's estimate of shuttle reliability, roughly 1 failure in 100,000 flights, with the engineering community's estimate, which was closer to 1 in 100. That's a factor of 1,000 difference, and it tells you everything about the disconnect between the people building and maintaining the hardware and the people making programmatic decisions. Feynman wrote, "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." That line gets quoted a lot, and it deserves to be, because it captures the essential truth of every disaster we've talked about so far. The redesigned solid rocket booster joint added a capture feature that limited how much the joint could open, a third O-ring, and heaters to keep the joint above a minimum temperature. The fixes were mechanical, but the deeper fixes, or at least the attempted deeper fixes, were organizational. NASA restructured its safety oversight. They created the Office of Safety, Reliability, and Quality Assurance, reporting directly to the NASA administrator, taking it out of the chain that had allowed safety concerns to be filtered and diluted as they moved up the hierarchy. The Rogers Commission explicitly called out the flawed decision-making process and the pressure on engineers to reverse their professional judgment. And yet, 17 years later, on February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry, killing all 7 crew members. The proximate cause was different. A piece of foam insulation had broken off the external tank during launch and struck the leading edge of the left wing, creating a hole in the reinforced carbon-carbon thermal protection panels. During re-entry, superheated plasma entered the wing through that hole and destroyed the internal structure. The shuttle lost control and disintegrated over Texas and Louisiana. But the systemic cause? The Columbia Accident Investigation Board found the same patterns. Normalization of deviance. Foam shedding had happened on multiple previous flights and had come to be seen as a maintenance issue rather than a safety of flight concern. Schedule pressure. Communication failures between engineers who were worried and managers who weren't listening. The board explicitly stated that the organizational causes of Columbia were remarkably similar to those of Challenger. The same agency, the same fundamental cultural problems, 17 years of supposed reform, and the same pattern reasserted itself. That's a sobering thing to sit with. It suggests that fixing organizational culture is harder than fixing O-rings. You can redesign a joint. Redesigning how thousands of people communicate, prioritize, and make decisions under pressure. That's a different kind of engineering entirely. Let me bring this back to the thread that's been running through everything we've talked about tonight. The Tay Bridge failed because assumptions about wind loading were wrong and quality control was poor. The de Havilland Comet failed because the interaction between pressurization cycles and stress concentrations at square windows wasn't understood. Aloha Airlines 243 failed because maintenance programs hadn't caught up with the reality of high cycle fatigue in aging aircraft. The Hyatt Regency walkways failed because a design change wasn't properly reviewed. And Challenger failed because engineers who understood the risk were overruled by a system that had gradually learned to tolerate warning signs. Each of these disasters taught us something specific and technical. But they also taught us something about how engineering actually happens in the real world, in organizations, under budgets, on schedules, with imperfect communication between imperfect humans. And that's what makes the next disaster we should talk about so fascinating, because it involves a structure that was, by every measure, a triumph of modern engineering. It was designed with enormous care, analyzed with sophisticated computer models, built with excellent materials, and inspected regularly. And it still failed, because the one thing the designers didn't fully account for was the wind. Not wind in general. They knew about wind. They'd accounted for wind in their calculations. What they hadn't fully grasped was how wind would interact with the specific geometry of the structure in a way that turned a steady breeze into a destructive, rhythmic force. And the structure I'm talking about is the Tacoma Narrows Bridge. Now, you've probably heard of this. 1. There's famous footage, grainy black and white film from November 7th, 1940, showing a suspension bridge in Washington state twisting and undulating like a ribbon in a storm. The roadway pitching back and forth, rippling in waves, until finally the whole center span tears itself apart and drops into Puget Sound. It's one of the most widely shown pieces of engineering failure footage in history. Every physics class, every introductory engineering course, someone puts that film on and says the words resonance or wind-induced vibration. But the real story is richer and stranger than a simple classroom demonstration, and it connects to everything we've been talking about tonight in ways that might surprise you. The Tacoma Narrows Bridge opened on July 1st, 1940. It spanned the Tacoma Narrows, a stretch of Puget Sound in Washington state connecting the city of Tacoma to the Kitsap Peninsula. The main span was about 2,800 feet long, which made it the third longest suspension bridge in the world at the time. It was designed by Leon Moisseiff, and here's where the human story gets interesting, because Moisseiff wasn't some unknown or careless engineer. He was one of the most respected bridge designers in America. He'd been a consulting engineer on the Manhattan Bridge, the George Washington Bridge, the Golden Gate Bridge. He was a pioneer in what's called deflection theory, a mathematical approach to analyzing how suspension bridges flex under load. His work had helped make longer, lighter, more elegant suspension bridges possible. He was, in many ways, at the cutting edge of his field. And that's exactly the problem. Moisseiff pushed the design of the Tacoma Narrows Bridge towards slenderness and elegance in a way that hadn't been tried before at that scale. The bridge deck was only 8 feet deep. The stiffening girders along the sides were shallow plate girders, rather than the deep, open trusses that older suspension bridges used. Think about what that means visually. If you looked at the Golden Gate Bridge from the side, you'd see a deep, lattice-like truss structure supporting the roadway, with lots of open space for wind to pass through. The Tacoma Narrows Bridge, by contrast, had solid, flat sides, almost like a wall running along each edge of the roadway. It was sleek. It was modern. It was also, essentially, a very long, very narrow, very flexible plate suspended in a windy gorge. The problem started almost immediately. Even during construction, workers noticed the bridge deck moving in the wind. Once it opened to traffic, the undulations became a regular feature. The bridge would bounce and ripple in moderate winds, not violently, but enough that driving across it felt like riding a roller coaster. Locals started calling it Galloping Gertie. Some people actually drove across it specifically for the thrill. Imagine that. A brand new piece of critical infrastructure, and people are treating it like an amusement park ride. Engineers were concerned, though. The Washington Toll Bridge Authority brought in consultants. They tried various fixes: hydraulic dampers attached to the cables, tie-down cables anchoring the deck to concrete blocks on the shore. Nothing worked particularly well. The bridge kept moving. And then came November 7th. That morning, winds in the Narrows picked up to around 42 miles per hour. That's a strong wind, sure, but it's not extraordinary. It's not a hurricane. It's the kind of wind that a well-designed bridge should handle without any drama at all. But the Tacoma Narrows Bridge didn't just bounce that morning. It started doing something different. Instead of the vertical undulations that people had gotten used to, the up and down bouncing. The bridge began to twist. The deck started rotating along its length, one side lifting while the other dropped, then reversing. The twisting motion grew more and more violent. At its worst, the two edges of the roadway were moving in opposite directions by as much as 28 feet. Think about that. You're standing on one side of a 39-foot wide roadway, and the other side is 28 feet higher or lower than you. The bridge was essentially wringing itself like a towel. The last car to make it off the bridge belonged to a newspaper editor named Leonard Coatsworth, who abandoned his car partway across and crawled on hands and knees along the tilting roadway to reach solid ground. His car, and a dog that was inside it, a cocker spaniel named Tubby, sadly, went down with the bridge when the center span finally broke apart around 11 a.m. The only fatality was that dog. It's a small mercy, really, that the bridge had been closed to traffic earlier that morning when the oscillations became clearly dangerous. Now, here's where the engineering explanation gets interesting, and where the common classroom version of the story gets it slightly wrong. You'll often hear the Tacoma Narrows collapse explained as a simple case of resonance. The wind happened to gust at the bridge's natural frequency, and the oscillations built up until the structure failed, like a singer shattering a wine glass with a sustained note at just the right pitch. But that's not quite what happened. The wind that morning was steady, not gusting rhythmically. It wasn't pulsing at the bridge's natural frequency. Something else was going on. What actually destroyed the Tacoma Narrows Bridge was a phenomenon called aeroelastic flutter. And this is where we need to slow down a bit, because understanding flutter is understanding something profound about how structures interact with the air around them. Think of it this way. When a steady wind hits a flat surface, like those shallow plate girders on the sides of the bridge deck, the airflow separates and creates vortices. These vortices create alternating areas of low pressure on one side and then the other, which push and pull on the structure. This is called vortex shedding, and it's related to why a flag flaps in a steady wind or why telephone wires hum. Now, if the structure is flexible enough to move in response to those aerodynamic forces, its motion changes the angle at which the wind hits it, which changes the aerodynamic forces, which changes the motion, which changes the forces again. You get a feedback loop. The structure's own movement is feeding energy back into the system. In the case of the Tacoma Narrows Bridge, the shallow, solid-sided deck was essentially acting like an airfoil, like a wing. And just as a wing can flutter if it's not properly stiffened, you've probably seen footage of aircraft wings oscillating dangerously in wind tunnel tests. The bridge deck entered a self-excited torsional flutter mode. The twisting motion changed the angle of attack of the wind on the deck, which generated forces that drove more twisting, which changed the angle further. Once the wind speed crossed a critical threshold, the energy being pumped into the system by this feedback loop exceeded the energy being dissipated by the bridge's structural damping, and the oscillations grew without bound. The bridge was literally tearing itself apart by interacting with a steady wind. Here's the thing that makes this so important for engineering history. The tools Moisseiff used to design the bridge, deflection theory, static load analysis, were perfectly good for calculating how the bridge would handle the weight of traffic or the direct push of wind pressure. But they didn't account for this dynamic, self-exciting interaction between the structure and the airflow. Nobody's tools did, really. Aerodynamic flutter was understood in the context of aircraft wings. The aerospace engineers knew about it, but bridge engineers hadn't yet connected those dots. The disciplines were separate. The knowledge existed, but it was in a different building, so to speak. After the collapse, everything changed. A massive investigation was launched, led by a commission that included the great structural engineer Othmar Ammann, who had designed the George Washington Bridge, and the aerodynamicist Theodore von Karman, who was one of the leading experts on fluid dynamics in the world. Von Karman was the one who really drove home the aerodynamic explanation. He'd already done pioneering work on vortex streets, the alternating patterns of vortices that form behind bluff bodies in a flow, now called von Karman vortex streets. He understood immediately that this was an aerodynamic problem, not just a structural one. The investigation's findings fundamentally reshaped how suspension bridges were designed. From that point forward, bridge aerodynamics became a critical design consideration. Wind tunnel testing of bridge deck cross-sections became standard practice. Designers moved away from solid plate girders and toward open truss stiffeners or streamlined box sections that were aerodynamically stable. When you look at modern suspension bridges, the Severn Bridge in England, completed in 1966, or the Great Belt East Bridge in Denmark, finished in 1998, or the Akashi Kaikyo Bridge in Japan, the longest suspension bridge in the world. Their deck sections are carefully shaped to manage airflow. They're designed not just to be strong enough, but to be aerodynamically stable. That's a direct legacy of Galloping Gertie. And think about what this failure teaches us in the context of our larger story tonight. Moisseiff didn't make a careless mistake. He didn't cut corners. He didn't use bad materials or ignore known principles. He applied the best analytical tools available to him, tools he himself had helped develop. And those tools simply didn't capture the phenomenon that destroyed his bridge. The knowledge gap wasn't about laziness or negligence. It was about the boundaries of what the profession understood at that time. The bridge failed at the frontier of knowledge. But there's a human cost to this story that's easy to overlook. Moisseiff's career was effectively destroyed. He'd been one of the most prominent bridge engineers in America, and the Tacoma Narrows collapse became permanently associated with his name. He died in 1943, just 3 years after the collapse. His reputation diminished. It's a reminder that behind every engineering failure, there are real people whose lives are changed forever. Not just the victims, but the designers, the builders, the inspectors. Engineering is a profession where your mistakes can be catastrophically public. Now, the Tacoma Narrows story is often treated as a standalone cautionary tale, the bridge that danced itself to death. But what makes it so relevant to everything we've been discussing is the pattern it fits into. Just like the comet disasters revealed the importance of fatigue in pressurized aircraft structures, the Tacoma Narrows collapse revealed the importance of aeroelastic effects in long-span bridges. Both were cases where pushing into new territory, longer spans, higher altitudes, greater pressurization, exposed phenomena that previous experience hadn't encountered. And both led to fundamental shifts in how engineers approach design. After the comets, you test for fatigue. After Tacoma Narrows, you test for aerodynamic stability. The knowledge gets encoded into standards, into textbooks, into the culture of the profession. But here's what keeps nagging at me, and it connects to what Diane Vaughan described with the normalization of deviance. The Tacoma Narrows Bridge bounced for 4 months before it collapsed. 4 months of visible, obvious, anomalous behavior. People drove across it and felt it move. Engineers were called in. Fixes were attempted. And yet the bridge stayed open. Traffic kept flowing. The anomaly was noted, studied, partially addressed, but not treated as the existential warning sign it actually was. Does that Sound familiar? O-ring erosion that wasn't supposed to happen but kept happening. Foam strikes that weren't supposed to cause damage but kept occurring. A bridge that wasn't supposed to move but kept galloping. In each case, the warning signs were visible, and in each case, the system found ways to continue operating in the presence of those warnings. Which brings us to something that happened much more recently, and much closer to the lives most of us live every day. Because the next failure I want to talk about doesn't involve a bridge or a spacecraft or an aircraft. It involves a building, specifically a condominium tower in a place where millions of people live in similar structures, a place where the ocean air carries salt and moisture into every crack and crevice of every concrete structure along the coast. And the warnings in this case didn't last 4 months. They lasted years, decades really, and the building came down anyway. The place was Surfside, Florida, a small beachfront town just north of Miami Beach, tucked between the Atlantic Ocean and Biscayne Bay. And the building was Champlain Towers South, a 12-story residential condominium completed in 1981. It had 136 units. Families lived there, retirees, young professionals, people who loved the ocean view, the sound of waves, the warm salt breeze drifting through their balcony doors at night. It was the kind of building you'd see all along that stretch of coastline. Reinforced concrete frame, flat plate slab construction, nothing exotic, nothing unusual. Thousands of buildings like it line the shores of South Florida, and on June 24th, 2021, at about 1:17 in the morning, while most of its residents were asleep, a substantial portion of Champlain Towers South collapsed. It didn't topple sideways. It didn't lean. It pancaked, floors falling onto floors in a progressive collapse that took roughly 12 seconds. 98 people died. Most of them were in their beds. And here's the thing that makes this disaster so deeply unsettling and so relevant to everything we've been talking about. This wasn't a case where nobody saw it coming. This wasn't a hidden flaw, a microscopic crack, an invisible phenomenon that only revealed itself in the moment of failure. The deterioration of Champlain Towers South was visible, documented, reported, discussed, debated, and deferred for years and years and years. Let me walk you through it, because the engineering story here is both straightforward and heartbreaking in its simplicity. Reinforced concrete is one of the most common building materials on Earth. You encounter it everywhere: parking garages, apartment buildings, bridges, dams. The idea is elegant. Concrete is incredibly strong in compression, meaning it handles being squeezed very well, but it's weak in tension. It doesn't like being pulled or stretched. Steel, on the other hand, is excellent in tension, so you embed steel reinforcing bars, rebar, inside the concrete, and now you have a composite material that handles both compression and tension. The concrete protects the steel, and the steel reinforces the concrete. It's a beautiful partnership, but that partnership depends on one critical thing. The concrete has to actually protect the steel. And this is where South Florida's environment becomes a problem. Concrete is porous. It's not a solid, impervious barrier. It's more like a very dense sponge at the microscopic level. Water can seep into it. And when that water carries chloride ions, which is exactly what happens when you're building next to the ocean, where salt spray is constantly in the air, those chlorides can eventually reach the embedded steel rebar. And when chlorides reach steel in the presence of moisture and oxygen, the steel corrodes. It rusts. Now, rusting steel doesn't just get weaker, it also expands. Iron oxide, rust, takes up significantly more volume than the original steel, something like 2 to 6 times more depending on the specific oxide formed. So as the rebar rusts, it swells, and that swelling pushes outward against the surrounding concrete. The concrete cracks. Those cracks let in more water and more chlorides, which accelerates the corrosion, which causes more swelling, which causes more cracking. It's a vicious cycle, a positive feedback loop. Engineers call it corrosion-induced spalling, and if you've ever seen a concrete structure near the ocean with chunks of concrete falling away, exposing rusty rebar underneath, that's what you're looking at. It's incredibly common in coastal environments, and it's manageable, but only if you actually manage it. Only if you inspect, maintain, and repair. Champlain Towers South had this problem from relatively early in its life. The building sat on a concrete slab that served as the floor of the pool deck and the ceiling of the underground parking garage below. This slab was essentially flat, and here's a design detail that mattered enormously. The pool deck slab was built essentially level, without adequate slope for drainage. Water, rainwater, pool water, whatever, didn't drain off efficiently. It ponded, it sat there, and over time, it found its way through the concrete. In 1994, a consulting engineering firm conducted a study of the building and noted that the pool deck slab had major structural damage. They documented cracking. They documented evidence of water intrusion into the parking garage below. You could see the staining, the mineral deposits, the evidence of water seeping through concrete that was supposed to be keeping it out. They noted that the waterproofing beneath the pool deck was failing and needed to be replaced. They noted deterioration of concrete columns and beams in the parking garage. And here's the critical part. The report stated that the failure to maintain the waterproofing was causing major structural damage to the concrete structural slab below the pool deck. Not cosmetic damage, structural damage. That word, structural, matters. It means load-bearing capacity is being compromised. That was 1994, 27 years before the collapse. Now, to be fair, the report recommended repairs, and some repairs were made over the years. But the fundamental waterproofing problem, the flat pool deck that ponded water, the failed membrane that was supposed to keep water away from the structural concrete below, that was never comprehensively addressed. The condo association, like condo associations everywhere, had to balance the cost of major structural repairs against the assessments that residents would have to pay. These weren't cheap fixes. Replacing waterproofing membranes, repairing structural concrete, addressing corroded rebar, we're talking about millions of dollars. And the residents were the ones who'd have to write those checks. So the work got discussed, debated, partially funded, partially deferred, discussed again, debated again, year after year. In 2018, as part of the building's required 40-year recertification process, Dade County requires buildings to undergo a structural inspection at 40 years and every 10 years after. Another engineering firm, Morabito Consultants, conducted an inspection. Their report, delivered in October 2018, was alarming. Frank Morabito's team found abundant cracking and spalling in the concrete columns, beams, and walls of the parking garage. They found evidence of ongoing water intrusion, and they found that the main issue, the waterproofing failure under the pool deck, had only gotten worse. The report stated that the failed waterproofing was causing major structural damage to the concrete structural slab below these areas, and that failure to replace the waterproofing in the near future would cause the deterioration to expand exponentially. That word, exponentially, should have been a fire alarm. It meant the problem wasn't just continuing, it was accelerating. But the report also noted that some of the damage could still be repaired if action was taken. It laid out recommendations. And again, the condo association began the slow, painful process of getting bids, getting approvals, figuring out how to pay for it. By 2021, they were finally moving toward beginning the repair work. Contractors were being engaged. Assessments were being levied on residents. The 40-year recertification process was underway. They ran out of time. Think about that timeline for a moment. The first documented warning was in 1994. The more urgent warning came in 2018. The collapse happened in 2021. That's 27 years from the first report, 3 years from the second. And throughout all of that time, people were living in the building, sleeping in their beds, raising children, growing old, trusting that the structure around them was sound. The National Institute of Standards and Technology, NIST, launched a full investigation, similar in scope and rigor to the investigations we've talked about for the comets, for the shuttle disasters, for every major engineering failure that demanded answers. Their investigation, which took years and involved detailed analysis of the physical evidence, construction documents, and structural modeling, concluded that the initial failure likely originated in the pool deck area. Specifically, that a portion of the pool deck slab failed first, and that this initial collapse damaged or removed critical structural supports for the main building, triggering the progressive collapse of the residential tower above. The mechanism is sobering in its straightforwardness. The concrete slab had been losing structural capacity for years due to corrosion of the reinforcing steel. The connections between the slab and the columns, the punching shear connections, which is how a flat slab transfers its load to the columns that support it, had been weakened. Punching shear failure is exactly what it sounds like. The column essentially punches through the slab, like pushing a pencil through a sheet of wet paper. When the concrete around a column is degraded and the rebar is corroded, the slab's ability to resist that punching force is compromised. And once one connection fails, the load it was carrying has to go somewhere. It transfers to the neighboring connections, which may already be weakened. And if they can't handle the extra load, they fail too. It's a zipper effect. One connection goes, then the next, then the next. And suddenly you have a large area of slab falling. And that falling mass impacts the structure below with enormous force, and the progressive collapse begins. There's nothing exotic about any of this. Reinforced concrete design, punching shear, corrosion protection, waterproofing. These are fundamental, well-understood aspects of structural engineering. The engineering knowledge to prevent this existed long before Champlain Towers South was built. The maintenance knowledge to catch and repair the deterioration existed decades before the collapse. What failed wasn't the engineering science. What failed was the system that was supposed to ensure the science was applied. The inspection regime, the maintenance funding, the decision-making process that allowed critical repairs to be deferred year after year. And this is what connects Surfside to every other disaster we've talked about. The technical cause is always specific: O-rings, fatigue cracks, aeroelastic flutter, corroded rebar. But underneath the technical cause, there's almost always an organizational, institutional, or human cause that allowed the technical problem to grow unchecked. At Champlain Towers South, the organizational failure was diffuse. It wasn't one person's decision. It was a collective, slow-motion failure of a system. A condo association trying to manage costs, residents, resisting expensive assessments, a regulatory framework that required inspection but had limited power to compel timely repairs. A broader culture in coastal construction that treated concrete deterioration as a maintenance nuisance rather than a safety emergency. After Surfside, the state of Florida passed new legislation requiring more frequent structural inspections for condominium buildings, particularly those near the coast. Condo associations were given new requirements for reserve funding, meaning they could no longer defer maintenance by simply not saving money for it. Other states and municipalities began reviewing their own inspection requirements. The engineering profession renewed its focus on the durability of existing concrete structures, on the importance of inspection and maintenance, and on the communication gap between engineers who write reports and the building owners and associations who have to act on them. Because that's one of the most painful aspects of the Surfside story. The engineers did write the reports. Frank Morabito's firm did identify the problem and did use urgent language, but a report is only as effective as the response it generates. And in a system where the people receiving the report are volunteer board members of a condo association, people who may not have engineering backgrounds, who are balancing the concerns of dozens or hundreds of residents who don't want to pay tens of thousands of dollars in special assessments, in that system, urgent engineering language can get diluted, deferred, reinterpreted. It's the normalization of deviants wearing different clothes. Instead of NASA managers redefining acceptable risk for O-ring erosion, you have a building community gradually accepting that the garage ceiling leaks, that the concrete looks rough in places, that the repairs will happen eventually, that the building has stood for decades, so it must be fundamentally okay. The anomaly becomes the new normal. The warning becomes background noise. And this brings us to something that I think is one of the most important and least discussed aspects of engineering safety. Something that connects not just to buildings and bridges and aircraft, but to every piece of infrastructure that surrounds you right now, holding up the world you live in. Because the truth is, most of the engineering failures that will matter in the coming decades won't come from new designs pushing into unknown territory, the way the comets did or the way Moissef's bridge did. They'll come from aging infrastructure, structures and systems that were built decades ago, that have been quietly deteriorating, and that depend on inspection, maintenance, and renewal to remain safe. And the question of whether that maintenance happens isn't really an engineering question at all. It's a question about money and politics and priorities, and whether we as a society are willing to pay for the invisible work of keeping things standing that we've already built, which is maybe the least glamorous topic in all of engineering, but also maybe the most important one, because glamour doesn't keep bridges from falling down. Glamour doesn't keep water mains from bursting under city streets. Glamour doesn't keep the electrical grid humming on a hot August afternoon when everyone's running their air conditioning and the transformers are 40 years old and nobody's replaced them because replacing transformers doesn't win elections. Nobody cuts a ribbon at a transformer replacement ceremony. Nobody names a highway after the engineer who recommended resealing expansion joints on schedule. And yet, that invisible, unglamorous, relentlessly mundane work of maintenance, that's the work that actually keeps people alive. Let me give you a number that might surprise you. The American Society of Civil Engineers publishes a report card every few years grading the condition of infrastructure in the United States across various categories: bridges, roads, dams, drinking water systems, wastewater, aviation, rail, all of it. In their 2021 report, the overall grade was a C-. That's the cumulative grade for the physical systems that an entire nation of over 300 million people depends on every single day. C-. Some individual categories were worse. Dams got a D, transit got a D-, roads got a D, drinking water got a C-. And look, these grades aren't arbitrary. They're based on condition assessments, capacity evaluations, funding gaps, and the age of the systems in question. When civil engineers are telling you that the nation's infrastructure earns a D in multiple categories, that's not alarmism. That's professionals looking at the data and saying, we are falling behind, and the gap between what we're spending on maintenance and what we need to spend is growing every year. The estimated investment gap, the difference between what's needed and what's actually being funded, was something like $2.5 trillion over a 10-year period as of that 2021 report. $2.5 trillion. That's a staggering number, and it's the kind of number that's so large it almost loses meaning. So let's make it smaller and more concrete. Think about a bridge. Not a famous bridge, not the Golden Gate or the Brooklyn Bridge, just an ordinary highway overpass, the kind you drive over or under every day without thinking about it. There are more than 600,000 bridges in the United States. As of recent assessments, something like 42,000 of them were classified as structurally deficient. Now, structurally deficient doesn't necessarily mean the bridge is about to collapse. It means that one or more key components have deteriorated to the point where they need significant repair or replacement. It means the bridge is still standing, still carrying traffic, but it's not in the condition it should be. It's aging, and the maintenance hasn't kept up. And here's the thing about bridges, and really about all infrastructure. Deterioration isn't linear. It's not like a bridge loses 1% of its capacity every year in a nice steady decline. Deterioration accelerates. A small crack lets in water. The water reaches the steel reinforcement. The steel starts to corrode. Corroding steel expands. Iron oxide takes up more volume than the original iron. And that expansion creates pressure inside the concrete, which causes more cracking, which lets in more water, which accelerates the corrosion. It's a feedback loop. The longer you wait, the worse it gets, and the more expensive the fix becomes. A repair that might cost $100,000 today could cost $2 million in 10 years if you let it go. And in 20 years, you might not be repairing the bridge at all. You might be replacing it entirely at a cost of tens of millions. Every dollar you defer in maintenance, you pay back with interest, compounded by physics. This is exactly what happened at Surfside. The repairs flagged in that 2018 Morabito report. The waterproofing, the concrete restoration, the structural reinforcement would have cost somewhere in the range of $9 to $15 million, depending on scope. That's a lot of money for a condo association, no question. But the building itself was worth hundreds of millions in real estate value, and the cost of the collapse, 98 lives, the demolition of the remaining structure, the legal settlements that eventually totaled over $1 billion, the trauma to an entire community. The cost of not doing the repairs was incalculably greater. It always is. Deferred maintenance is the most expensive kind of maintenance there is, because eventually the bill comes due, and it comes due with lives attached. And this pattern repeats everywhere, in every category of infrastructure. Think about water systems. Many American cities are still served by water mains that were installed in the late 19th or early 20th century. Cast iron pipes, some of them over 100 years old, buried under streets that have been paved and repaved, carrying water to homes and businesses every day. These pipes corrode. They develop leaks. The American Water Works Association has estimated that the country loses about 6 billion gallons of treated drinking water every single day to leaks in aging distribution systems. 6 billion gallons a day, just leaking into the ground. That's treated water. Water that's already been pumped, filtered, chemically treated, and pressurized, all of which costs energy and money. And when a main finally breaks, which happens about 240,000 times a year in the US, you get flooded streets, boil water advisories, sinkholes, disrupted traffic, damaged property. Each break is a small crisis, and each one was preventable in principle, with timely replacement of aging pipe. But here's the question: who pays for it? And this is where engineering meets politics, and where the story gets complicated in a different way than any of the disasters we've talked about tonight. Because the engineering knowledge exists. We know how to build good water systems. We know how to inspect bridges. We know how to maintain concrete structures so they last 100 years or more. The knowledge isn't the bottleneck. The bottleneck is the willingness to fund the work. And that willingness depends on political systems, on budget priorities, on whether voters and elected officials see infrastructure maintenance as important enough to spend money on. Money that could also go to new programs, tax cuts, visible projects with ribbon-cutting potential. Maintenance is invisible when it's done well. You only notice infrastructure when it fails, which creates a perverse incentive structure where the political reward for maintaining things is essentially zero, and the political cost of failure only arrives after it's too late. There's a concept in public policy sometimes called the infrastructure trap, and it works like this. A new piece of infrastructure gets built: a bridge, a water treatment plant, a highway. It's shiny and new, and everyone's happy. For the first 10 or 20 years, it needs minimal maintenance. Everything works fine. The public takes it for granted. Then, it starts to age. It needs investment, not dramatic investment, just steady, consistent funding for upkeep. But that funding competes with other priorities. It's easy to defer. The bridge still looks okay from the outside. The water still flows. So the maintenance budget gets trimmed or delayed or redirected, and for a while, nothing bad happens, which reinforces the idea that the cuts were fine. Sound familiar? It's normalization of deviance again, just operating at the scale of public budgets instead of NASA meeting rooms or condo board votes. And then, decades later, you're facing a crisis. The infrastructure has deteriorated to the point where it needs massive investment, far more than the steady maintenance would have cost. But now the price tag is so large that it's politically difficult to fund. So you do partial fixes, band-aids. You repair the worst sections and hope the rest holds. And the cycle continues. This is happening right now, all over the world, in every developed country that built aggressively in the mid-20th century and is now watching that infrastructure reach the end of its design life. I think about this a lot, honestly, because when we started tonight, we were talking about the ancient Romans, about that amphitheater at Fidenae that collapsed because someone cut corners on the foundations. And in a way, the story of engineering disasters has always been the same story, told over and over with different materials and different scales. Someone builds something ambitious. Somewhere in the process, in the design, in the construction, in the maintenance, in the oversight, something gets missed or ignored or deferred, and the structure holds for a while because most structures have some margin of safety built in, some reserve capacity that can absorb a certain amount of neglect. But that margin isn't infinite, and when it's finally exhausted, the failure can be sudden and catastrophic. even though the causes were gradual and slow. The Tay Bridge didn't fall because of one storm. It fell because of design flaws and poor construction quality that had been present since the day it was built, waiting for the right conditions to reveal themselves. The de Havilland comets didn't break apart because of one flight. They broke apart because of fatigue cracks that had been growing, cycle by cycle, flight by flight, from stress concentrations that the designers hadn't fully understood. Challenger didn't explode because of one cold morning. It failed because of an organizational culture that had been gradually accepting more and more risk, meeting by meeting, launch by launch, until the margin was gone. And Champlain Towers South didn't collapse because of one night's events. It collapsed because of decades of corrosion and deterioration that had been documented, reported, discussed, and ultimately not addressed. In every case, the seeds of the disaster were planted long before the disaster happened. And in every case, there were moments, sometimes many moments, when the outcome could have been different. If someone had listened, if someone had insisted, if the money had been spent, if the culture had been different. Engineering disasters are almost never purely technical failures. They're failures of systems, systems that include not just steel and concrete and physics, but people, organizations, incentives, communication, and values. And that's maybe the most important thing to carry with you from everything we've talked about tonight. Not the specific details of any one disaster, though those matter. Not the technical mechanisms, though understanding those is important. But the deeper pattern, the recognition that safety isn't something you achieve once and then have forever. It's something you maintain. It requires constant attention, constant investment, constant willingness to hear bad news and act on it. It requires the kind of boring, unglamorous, day in day out vigilance that never makes headlines but keeps the world from falling apart. And you know what? That work is happening right now, tonight, while you're lying here listening to this. Somewhere, a bridge inspector is writing up a report on a hairline crack they found in a steel girder. Somewhere, a water utility engineer is reviewing flow data and flagging a section of pipe that's showing signs of wear. Somewhere, a building inspector is climbing into a crawl space with a flashlight, checking foundations. Somewhere, an aviation maintenance technician is running, their hands along the skin of an aircraft, looking for the faintest signs of fatigue. These are the people who keep the world standing. They don't get monuments. They don't get their names in history books. But every safe flight you've ever taken, every bridge you've ever crossed, every building you've ever slept in, you owe that safety, in part, to someone who did the quiet, invisible work of checking and maintaining and refusing to let the anomaly become the new normal. So as you drift off tonight, surrounded by the engineered world, the walls around you, the roof above you, the electrical system humming quietly, the water pressure waiting patiently in the pipes, know that all of it represents accumulated knowledge, hard-won through centuries of trial and error, of ambition and failure, of people who built things and people who figured out why those things broke, and people who made sure the next version was better. Every building code, every safety regulation, every inspection protocol. Those aren't just bureaucratic paperwork. They're lessons written in the language of loss, each one tracing back to a moment when something went wrong and someone said, "Never again." And the story isn't over. It never is. Engineering keeps evolving, keeps pushing into new territory, keeps finding new ways to fail and new ways to learn. But the fundamental bargain remains the same as it's always been. We build ambitious things, and in return, we accept the responsibility of maintaining them, inspecting them, and listening when they tell us something is wrong. That's the deal. That's the work. And it goes on, quietly, steadily, while the world sleeps.